Hello everyone, I'm happy to introduce the 12th session of the CEPR-EAERE webinar on climate policy. This time we will talk about carbon pricing under uncertainty. It's a more technical topic than usual for this webinar, but I'm happy to see that you remain very much interested by this. Even if you dislike carbon tax or market for permits, we need a carbon value if we want to do benefit cost analysis to determine what kind of action should be implemented in order to reduce emission. We need a carbon value. So this carbon value should be equal to the present value of the marginal damage generated by CO2. And the problem is those damages are typically uncertain. We are sure. Look at the last opus of the IPCC. We are now certain that climate change comes from emitting greenhouse gases in the atmosphere, but we are still quite uncertain about the intensity of the phenomenon. And so that is a difficult question to determine the social cost of carbon. Well, I'm very happy to see that compared to the debate we had here 10 or 15 years ago after the publication of the report by Nicolas Stern, and this debate between William Nordhaus and Nicolas Stern, well, this debate was not very deep. Mostly we talk about the Ramsey rule to think about what the discount rate should be used in order to value this flow of marginal damages. Now we have a new generation of research, and let me say also a new generation of researchers to work more deeply about this issue, and in particular to combine asset pricing methodology with climate economics. And so I'm very happy today to introduce 4 experts that have been working quite intensively over the last few years on this topic. So first, Aude Pommeret, who is at France Stratégie and professor at the Université de Savoie in France. And her coach, Frédéric Cherbonnier, my colleague at the Toulouse School of Economics. Then we will have a second presentation by Derek Lemoine. Derek is a professor at the University of Arizona. And eventually, last but not least, we will have Billy Pizer, professor at Duke University and a fellow of the Research for the Future. Before we start, let me just say a few words about the organization. Each presentation will last for 20 minutes, and then we will have 30 minutes for discussion. So don't hesitate to put questions on the chat. We will try to cover your question during the last part of this webinar. Without any further detail, let me give the floor to Frédéric Cherbonnier. Thank you very much.
Okay, thanks, Chester, for asking us to speak today. So this is a joint presentation with Aude in 4 parts. I will present the first and the last one, and Aude will present the 2 parts in the middle. So first, let's start saying that putting a value on carbon emission is very important to induce the right investment. Usually when one wants to decide about an investment, you need to compute what is called the net present value of future cost and benefit. It's amount to do what is called cost and benefit analysis. And what we want to do here is to take into account the project impact on climate change. A very basic example we will look at is consider an investment today that will define future CO2 emission by a volume delta T at time T. Delta may be positive, it's for instance to build a new highway or tollway inducing more pollution. It may be negative, it's about building a new renewable energy production. Now, in the following, what we will only consider project that has a marginal impact on consumption. And what is important in all those work is what is the damage induced by 1 ton of carbon dioxide emitted at a given time, let's say capital T. It would have a negative marginal impact on consumption that here we note that MD is 40 capital T. This marginal impact on consumption translates into a marginal impact on the utility of the representative consumer. And if we use a well-known first-order Taylor expansion, then we see easily that the marginal impact of the utility is simply the product of the marginal utility of consumptions times the marginal damage. So this number, the marginal damage, of course, it's a complex number. It's computed with evolved model, like integrated assessment model, and I will not deal with that explicitly here. Now let's consider a basic example, a project that has only as a consequence to reduce the emission by a given volume delta at only during 1 year at time capital T. If you want that to put in the net count value of the project, the benefit of reducing this emission, you need to sum all the reduced, the value of the avoided damage during all the subsequent years. So this is what is done in this basic formula. You have the marginal utility times the volume of emission at time capital T times the marginal damage that occurred later. We put in the beginning discount rate, which is the delta is the pure rate, pure preference for time, and we divide in the end by the marginal utility of consumption today in order to get a monetary equivalent. So this formula, when T equals 0 and when delta is just 1 ton of CO2, this is what is called the today social cost of carbon. Now, this social cost of carbon is what is fixed usually by a public administration to provide the right incentive. However, it's slightly different. The social cost of carbon at time T, usually it is the monetary equivalent at time T of damages induced by 1 ton of CO2 emitted at the same time T. So when T equals 0, it is what I have shown in the previous slide. When T is greater than 0, you need to discount. So you use an official social discount rate, again, fixed usually by public administration, and you use a very basic formula that is here to compute the net present value of the avoided damage. This is a simple formula, but it's not that simple, because when you look at the data from parameters given by the public administration, often both parameters, social cost of carbon and social discount rate, are not a result of mutually consistent evaluation. An easy way to see that is to ask the question, what is the optimal speed of CO2 emission reduction? If you look at French data, the official social cost of carbon curve has an increasing rate of 10%. And the social discount rate is about 3%. It means that the value of reducing or avoiding 1 ton of CO2 today is 7% lower than the value of avoiding 1 ton of CO2 next year. It's an incentive to procrastinate. It's quite surprising, and there's many explanations for that, and simply that the carbon social cost of carbon is a consequence of a political decision on a carbon budget, and not at all of an intertemporal optimization. If you look at the most recent report from the US Environmental Protection Agency, that have an opposite result. The growth of the social cost of carbon is quite low, about 1%. The interest rate, the social discount rate is close to 2%, which means that the present value of CO2 emission is decreasing over time, and better to act now than later. Here, this is a more robust result, because in the case of the US EPR report, the two parameters are the result of a joint evaluation. Now, even if you use those two parameters, it's important to notice that the equation 1 here is not correct if delta is uncertain. It's correct only if delta is certain. So I will give the floor to Maud, and I will come back to this issue at the end.
Yeah, so as a first step, if you want to properly account for benefits that are uncertain, you can focus on the risk-adjusted social discount rates. So the classical approach to compute the net present value of a project yielding net benefits BT that are uncertain is the following. So what you would like to do is to compute a present value by just taking the discounted sum of the expected benefit, as you see on the first equation. Okay, all the question is then, what do you put exactly in this RT? As we've seen before, the project has marginal impacts on consumption. So this present value should exactly be the equation 2 on the slide, which is the discounted sum, but using a pure preference for time delta when you discount, of the expectation of the product of the benefits time U prime of C, because they need to be evaluated using marginal consumption. And then you just divide by U prime of C0 in order to get something in euro at time 0. So these two present values should be equivalent. So if you just make them being equal, you end up with the equation at the end of the slide, which is the social discount rate expressed in a way that could look a little bit complicated if you are not familiar with that, but that's not really, in particular, if you take a special process for consumption. So if you take a geometric Brownian motion with a trend mu and volatility sigma, if you also assume a constant relative risk aversion gamma, then you end up with, so first you have a first part that is a risk-free discount rate, which is RF on this slide, and then I will add a risk premium part. So looking at this, this risk-free discount rate, it's basically what Christian Gaulier said in the introduction, that's the Ramsey rule. Here it's just extended in order to take into account the fact that the growth rate of the economy can be uncertain. So in this case, you have a precautionary effect to add. Basic idea behind the Ramsey rule is that if you expect future generation to be richer, then you should discount more. So then added to this risk-free rate, we should add a risk premium. And this risk premium is going to depend on two things. So it is following the consumption-based asset pricing model. And the two parts I was speaking of are first, the systematic risk premium. So this is a risk premium for aggregate consumption in the economy. And then everything depends on how much the benefits of our project are correlated with aggregate consumption in the economy. So this is a beta by association with what is done usually in finance. So this beta, we're going to be called consumption beta here, really is the elasticity of our benefits with respect to aggregate consumption. So how to interpret this beta? A very large beta means that the project gains value in terms of growth. So basically, we will have a project that delivers high benefits in case we have an economy that is going well, and it is going to have low benefits in case the economy is in trouble. So in this case, it reinforces the macroeconomic risk, and it's going to be typically the case of transportation projects. On the contrary, if we have a beta that is negative, it means that the project has an insurance value. On the contrary, the project is going to deliver high benefits in case the economy is not going very well, and it's going to have low benefits when the economy is booming. We can already have the intuition of the insurance value of such a project. And it's typically the case of hospitals or nuclear waste deep repository. So for instance, if we consider the very precise case of a motorway project, then first you will have economic benefits of this motorway, and then they will have a positive income elasticity. But you will have also negative externalities to account for, and they're proportional to both the road traffic and the marginal carbon damage. So how much emission do you have? It depends on the road traffic, and how much is the value of each of these emissions depends on the marginal carbon damage. Okay, and taking into account these two negative externalities is what has been in the literature designed as a climate beta. So the problem is that the beta is very complex to set. So for instance, one of the only countries that take a discount rate depending on beta, so that can change depending on the project, is France. So you can see the expression for France on the slide. The issue is that it is still an ongoing work to try to see, at least for different sectors, what the beta should be. In the UK, then you have a constant beta in general, so ended up with a discount rate, a social discount rate that is 3.5, except for project related to health. In this case, it's 1.5. But so you don't have something that is really dependent on beta. So to try to correctly account for the uncertainty on the benefits of the project, but at the same time try to do something not too complicated. We have proposed, so with Frédéric and Christian, so in this paper, stress discounting, a new method. So that's really going to be very simple. And it really allows to grasp this idea of insurance value, or on the opposite, to increase the macroeconomic risk. So here is a very basic principle. So an asset value is equal to the expectation of its contingent net present value over the multiple states of nature that characterize the asset. So the idea is that you take one state of nature, and then you can compute the present value of the project using just the Ramsey rule, no uncertainty. Okay, you know you are in this state of nature, so everything is very simple. And then you do that for an infinite number of states of nature. And once you've done that, you have all this present value, then you take the expectation over all the different states of nature. So if you do that, you have an exact value. The only problem is that you have a huge number of different states of nature, so it's not very practical. Our claim is the following. You can have a good approximation if you reduce the number of states of nature. So as an illustration, I will take the case where you only have two states of nature. One I will call the business as usual, and the other one, the stress scenario. And it's like a barotype catastrophe. So in this case, our present value, taking into account these two states of nature, is going first what is in blue in the equation, what's happening in the case we're in business as usual, and we discount, and this is a Ramsey rule. And what is happening when we are in the red case? Okay, that's the stress scenario. We take the discounted sum and we discount with something that is certain for the social discount factor. And then we just need to take the expectation with a probability pi on each of the scenarios. So that's really, really simple. We still need to calibrate a number of parameters. We leave the calibration to the evaluator. However, in particular, in the paper, for benchmarking purposes, we propose one that is consistent with the main characteristics of the yield curve. So based on this calibration, then we can benchmark this method with what is considered as a good but complex discounting method by project analysts, namely Martin's cumulant method. So with the cumulant, you can also take into account the possibility of catastrophe in the economy. So here is what we obtain. So on the horizontal axis, what you have is different values of beta between -1 and 1.5. And what is represented then is a present value of the project. We have a horizon that is 15 years. So what you can see is that the dashed line, so let's look at the black line first, is quite close to the one provided by Martin. And in particular, it's doing a lot better than what you obtain using UK method or the French method. So in particular, the UK method, there is only beta. Beta is not changing. So for real project with a negative beta that should have an insurance value, then it's not showing up with the UK method. Hence, there is a too low present value for negative beta project. On the contrary, for France, France is going to put a lot of weight on the different values of beta. So this is assuming France is able to actually have an idea about the value of beta. Then you see that it is overestimating the present value of projects that have an insurance value. So now we're going to turn to what is happening when we have a climate dimension explicitly in the project we consider.
Okay, now I will quickly show you how we can apply this method in the context of climate change. First of all, I need to say that you will see one slide, next slide, temperature increases, carbon value, and it's important to say it's not normative, it's just to illustrate the method. We think that it's up, as Aude said, up to the public administration to try to choose the right model, choose the right parameters. Here we are just illustrating the method. So the method is in 3 steps. You need first to choose a description of the economy of the climate. And here we are based on the diet model, slightly enriched take into account the two main sources of uncertainty, climate and economic growth. So I will quickly move to the next slide to show you first what type of scenario we choose. We have two types of risk, climate and economics. The climate risk corresponds to the choice of climate sensitivity. Climate sensitivity is how much the temperature of the planet will increase if we multiply by 2 the concentration of CO2 in the atmosphere. So we have a good scenario with a low climate sensitivity of 2.6 degrees Celsius, another one with a high climate sensitivity of 5.7%. And regarding economic growth, we have a good scenario with a high growth and a bad scenario with like a barrel disaster, a sudden drop of GDP followed by a slow decrease of GDP. And then it gives us 4 scenarios, good situation in both cases or bad in both cases and so on. And if you look at the left picture, it's the temperature increase. You see that the worst case is when you have a good economy and a bad climate, which is logic because when you have a good economy, you are producing a lot, and so you are polluting a lot. And so you have a higher rise in temperature. If you look at the right picture, it's the social cost of carbon. In that case, the highest total cost of carbon, at least on short-term horizon, is when you have both shocks, a bad economy and a bad climate. Why? Because simply when you have a bad economy, it means that future generations will be very poor, and so we need to make higher efforts to give for the future generation. So those parameters are chosen in order to mimic for the bad scenarios, the 8% worst cases in the considered distribution of climate sensitivity or economic growth. I will not go more in detail here. Now let's choose just one illustration. Let's look at what we would get with a basic project, a mitigation project that prevents the emission of 1 ton of CO2 each year every 50 years. The orange curve gives the exact value when we compute the value using Monte Carlo simulation, 10,000 Monte Carlo simulation. And the yellow curve gives the value given by the stress discounting method. You see it's very close. So the method is working very well. And beside gives us the contribution of each scenario. It's allowed to have a better interpretation of the value. And you see here that about 75% of the value of the project comes from catastrophic scenario. And nearly half of the value comes from the case where there is a bad economic situation, which means that a part of the value of the project is for the case where future generations are very poor. Besides the contribution of the low probability scenario where we have both economic and climate catastrophe is very significant. Then just to finish, we said about benchmarking. Here that's an example of benchmarking. On the left picture, we are looking at what is the present carbon value given by the method versus what is the present carbon value given by the Monte Carlo simulation. We see that it starts about $150 and it decreases slowly among the year, and the stress discounting method and the exact method are very close. However, of course, we could obtain the same data used by applying the correct social discount rate to the correct social cost of carbon. But it will not work for a project where the amount of emission or volume reduction of CO2 depend on the economic activity. You see on the right slide picture, you have the case where the elasticity of the volume of emission reduction is equal to 1 with respect to economic growth. In that case, the yellow curve is what you want to obtain if you do the back computation using this formula. The formula is used officially by administration. But this starts using the official social discount rate, the amount of emission times the total cost of carbon. And you see that you overestimate a lot the real value because you don't take into account the fact that the project has a high value while everything is fine regarding the economic situation. If you correctly adjust and take into account that the project is mainly useful when you have a good economic scenario, then the value of the project is only lower. And the stress discounting method allows to capture that. I think I run out of time, so I will stop here. Thanks.
Thank you, Frédéric. Thank you all. without further discussion, keep in mind that we will have a discussion at the end of the 3 presentation. I give the floor to Derek. Derek, the floor is yours.
Advising us, and thank you, Alder Federic, for the talk. I think this will dovetail nicely. So my talk's going to sort of fit in between the other two, in that I'm not going to go as much toward numbers and then give more a framework for the pieces of uncertainty, which then the other 2 papers are doing more of the calculations connected to that. So the first thing, I mean, obviously about climate change, there's uncertainty everywhere, and there's multiple layers of uncertainty. So there's uncertainty about what emissions are going to be in the future, and therefore what the driver of warming is going to be. There's a lot of uncertainty about what warming is going to be, partly due to emissions, partly due to just we don't know how sensitive the climate might be to each unit of emissions, which is part of the last talk. There's a lot of uncertainty about, I would argue most uncertainty about damages per unit of warming. What does climate change mean for the economy and for things that we care about? It's all an out-of-sample experiment. We haven't run it yet. Even after we've run it, it's kind of hard to know how we would really get the number right. So there's a whole extrapolation and projection exercise that's just fundamentally deeply uncertain. And then just future technology and consumption. We're looking at the world decades or even 100 or hundreds of years out, and anything could happen at some level. So uncertainty is probably critical to climate pricing. I think that's everybody's intuition, but integrated assessment models that we've used to assess the carbon price have traditionally struggled with that. So the benchmark models that we've used for decades now, for nigh on 30 years, really have been totally deterministic. There's no uncertainty inside of them. And those are the models that have often been the reference points for policy. One can take Monte Carlo analysis of these models, so basically run them under a bunch of different parameter possibilities and get this set of things that could happen, and then maybe try to choose a policy that'd be robust to that set of things that could happen. But a Monte Carlo analysis isn't the same thing as making the policy itself incorporate uncertainty. It's kind of showing what uncertainty might do with a given policy, but the policy itself isn't baking in uncertainty. It's not really the answer that we want. I'll also note there was a literature that began about 13 years ago, or really exploded around 13 years ago, on what's called recursive or dynamic programming versions of integrated assessment models. And these do uncertainty in the fully correct way, where there's learning. It's not just passive learning, it's active learning, where you control how fast you learn in an optimal fashion. These are kind of black boxy, they're computationally demanding. I think there's limitations that make it hard for them to be tools of applied policy analysis. So today, what we're going to do is I'm going to give a framework to think about how uncertainty matters. And then without getting into a particular calculation, I'm going to step back and think about how we can calculate that effect. And I'm going to highlight 2 ways that I think people intuitively want to do it that I think are incorrect, or I know are incorrect, and then 2 ways that I think are equivalent that are correct. And it's a matter of choice, which approach you'd like to use. So at a high level, I'm going to break each of these pieces out in a second. There's basically a few channels that uncertainty matters through. There's a precautionary channel that was highlighted in the previous talk. There's an insurance channel, the beta channel, that was highlighted in the previous talk. And I'm going to find it convenient to break the insurance channel up into 2 pieces for reasons that I'll touch on in a bit. This framework and this decomposition is going to follow my Jerry paper from 2021. Some parts of it will depend on functional form, and I'll try to make that clear, but I find it a useful way of thinking about it. If you want numbers, you can look at that paper as well, but I'll stay away from that. Okay, so first, the precautionary channel. So the last paper did a nice job of highlighting that. I want to drill down on that a little more. So whether the sign and the degree of the precautionary channel depend on whether agents are prudent and how prudent they are. What prudence is we call an agent prudent if I offer you 2 lotteries, one riskier than the other, and then I say you can attach a sure unit of consumption to one of these 2 lotteries. Would you rather get an extra $1 in the world where you're facing less risk, or an extra $1 in the world where you're facing more risk? A prudent agent is going to want to take the extra $1 in a world where they're facing more risk. They want to attach consumption to the riskier lottery. If you think about that in terms of the present versus the future is inherently somewhat riskier in the sense that, we already know the states of the present. We don't know the states of the future. And if I'm asking you whether you'd rather attach a sure dollar to the present or the future, then all else equal, you're going to rather attach it to the future just because it's riskier. Take that into climate. So then we think of emissions as a form of saving. So we've just said uncertainty makes us want to save a bit more than we otherwise would have. So therefore, we want to reduce emissions as ways of saving through the environmental bank, so to speak. Climatic and economic uncertainties make future or consumption even more uncertain than they would have been. So all these uncertainties in the last talk just kind of compound all the other uncertainties we have. And so the effect is going to be that we're going to increase desired emission reductions, desired emission savings, so to speak, and we're going to increase the social cost of carbon. Under the discount rate interpretation, what we're doing is we're lowering the risk-free discount rate. And this applies to any future payoff. So these climatic uncertainties are going to rate to use not just for climate change investments, emission reductions, but also for any investment, how you value any sort of new technology that might appear, any sort of highway that even without emission externalities. This risk-free rate adjustment applies across the board. Any stock, any bond, anything should be affected by it. Then there's also an insurance channel that's specific to climate change. So the idea of an insurance channel is general, and that's that you like assets that pay off well when you're otherwise doing poorly. If you're going to hold a stock that goes bonkers when you're otherwise rich, that's less desirable than holding a stock that goes bonkers when you're otherwise poor. You'd like to get the stock's payoff when you're out of a job. That's just a more valuable stock. So that correlation between how well the stock does and what your consumption is called the beta. And a positive beta makes something look riskier. A negative beta means it's a good hedge and not a bad hedge, and you want to pay more for it. So taking that into climate, the question is, will today's emission reductions benefit the future more in cases where the future ends up rich, in which case they're a bad hedge, or in cases where the future ends up poor, in which case they're a good hedge? And this is now going to end up being an adjustment to the discount rate. We're adjusting the risk-free rate from the previous slide for risk. And this adjustment is particular to climate investments. It could be a radically different adjustment, even opposite in sign to what you might see when you value a stock or a bond or the non-emissions parts of a highway or anything. This is a climate particular adjustment. And this is again highlighted in the previous talk. So what I'm going to do now is talk about the pieces of this insurance channel, and in a slide or two, it'll be clear why I want to break it up. So in general, the insurance channel is hard to sign. It's not clear. It could go either way. I mentioned that we know the sign on the precautionary channel. That's not true for the insurance channel. There's conflicting effects. I think in general, there's two main effects that are worth highlighting. So one is what I'm calling a damage scaling channel. So if you take the conventional way that we represent damages from climate change in economic models, those damages are what we call multiplicative with total output. That means that for a given amount of warming, your consumption loss, not your utility loss, but your consumption loss is going to be greater the more the output was in society. There's just more at stake. If there's barely any output in society, there's a bound on how big your losses could be. The more output you have, kind of the greater that loss consumption can be. So this mechanically makes emissions a bad hedge. If just mechanically you lose more from climate change when you have more, that means that climate change is more costly when you're richer. So mechanically, this channel is going to make emission reductions be a bad hedge and reduce our value of reducing emissions. But there's another piece of the insurance channel. So instead of thinking just about that level effect, we can also think about how the growth of output from period to period, sort of like netting out these level effects, is going to be affected by climate change. So now the question is, do additional emission reductions increase the growth rate of consumption, not just the level of consumption loss, by more when we're relatively poor or relatively rich? And I think there's two main stories that are worth considering. So the first, climate change might actually make us poor. So this could be the case if there's a lot more warming than expected, which is the case highlighted in the previous talk. Could be the case if there's exactly the warming we expected, but warming is just a lot worse for the economy than we expected. And either of those types of outcomes, we're poor because climate change was bad, or rich because climate change was not so bad. These sorts of uncertainties pretty clearly are going to favor reducing emissions because these are a good insurance value. The other prominent case is thinking about how our economic growth might itself drive climate change. So if we're growing really rapidly, then for given technology and given fuel use shares, that's going to tend to make atmospheric CO2 pretty high. So in general, CO2 is going to be high when we're rich. If we're not growing very rapidly, then that's going to tend to make CO2 lower, all else equal. So the trick here is that we need to think about how the marginal effect of today's emission reductions on future climate change varies with the level of CO2 in the atmosphere. In older models, the thought was that as CO2 gets higher, you have a smaller and smaller marginal effect on warming. Basically, you're closing off the window of outgoing radiation that carbon can trap. And the more carbon you've got up there, the increasing effect is as you got it at closing off the window. You've already closed off the bands at which are most effective at trapping heat, and you're kind of moving to more marginal bands. So under that story, today's CO2 emissions trap the most heat when atmospheric CO2 is otherwise low, which is exactly the case in which we end up poor. And again, emission reductions act like a good hedge. Some more recent scientific models suggest that, no matter what, you can just approximate warming as a linear function of past emissions. And in that case, this hedging effect just drops out entirely. So that last hedging effect's a little disputable, but at least the main one, the damage and warming uncertainty one, it's pretty clear that this channel makes climate change a good hedge, or makes emission reduction a good hedge. So what matters is the net effect. At some level, we don't really care about the sign of any individual channel. What we're trying to do is get the net effect. And so I think the really important point here is that we need to not think about just the insurance channel or just the precautionary channel. We need to always think about the combination of all of them. So at least in my model, and I think this is going to be true in most models, I could not sign the insurance channel itself. You don't know how the damage scaling and growth insurance channels net out. They typically oppose each other. In the insurance channel, the beta could be positive or negative. But I do show that once you break it apart, the precautionary savings channel and the damage scaling channel are commensurable with each other. And you can show that under standard preferences, the precautionary channel that works to raise the social cost of carbon is going to dominate the damage scaling channel. So these two things, a negative and a positive, are going to add together, and the positive is going to swamp out the negative, at least under standard preferences. So then if you know that, well, again, on that same model, the growth insurance channel is always positive. So now you've netted out the negative channel with a positive precautionary effect, and you're adding on this positive growth insurance channel. So the net effect of everything is going to increase the social cost of carbon, whether or not the beta is positive or negative, because if the beta is positive, and you would think that the insurance channel would work to reduce the social cost of carbon, this implies the precautionary channel is going to dominate the insurance effect in that case. So takeaways, so for calculations, and this is where I'm going to come to next, it's really, really critical that all the calculations include the precautionary adjustment and the insurance adjustment. You can't take one piece of it, or you could actually get the sign wrong. And Christian and Simon highlighted this effect in their paper as well, where they were focusing on the sign of the beta, and they mentioned that the sign of the beta actually might not be determinative about the social cost of carbon. So just as a graphical illustration of what I've said so far before you go into calculation, you can basically take a few types of uncertainty. You can break them apart into these precautionary and insurance effects. Insurance effects hard to sign in its own right, but once you've broken them apart, you can then get a net sign because different things clearly dominate each other. Okay, so let's think about some calculations you could do. So there has been work that has addressed the effect of uncertainty on climate policy by basically running models effectively in Monte Carlo fashion, and then assessing whether climate damages and consumption are correlated. And typically what you find from at least the parameterizations of these models, which I think it could change with different ones, but at least in those parameterizations, you find that you have more damages when consumption is high, when you're otherwise rich. Part of this is because economic growth makes climate change worse when you're rich. Part of it is because of this damage scaling effect. Damages are just mechanically larger when you're rich. I want to emphasize this is wrong for two reasons for thinking about the net effect of uncertainty. One is that we don't just need our damages big or small, we need the marginal effect of emissions on damages. And for reasons I just gave around those atmospheric physics, that doesn't even always go in the same direction. So that's really important. On top of that, even if that were not an issue, this is just about the insurance channel, and you also need to be thinking about the precautionary effect as well. Another thing that I have seen done and proposed is to calculate, take distributions from literature, from an econometric model or something, basically turn each uncertain parameter into a certainty equivalent loss from emissions. So now you've got a bunch of certainty equivalents that are taking account of curvature. So you're accounting for the effects of uncertainty that way. And then you aggregate these using standard Ramsey discount rates, take a present value, you've already basically taken expectations, and you've now got the value of reducing emissions. So you're basically getting rid of distributions kind of behind the scenes by taking certainty equivalents for consumption and then aggregating with a Ramsey rate, similar to what would have come out of the Stern report debate that Christian mentioned. The problem here is that the precautionary channel should reduce that discount rate that you're using to aggregate. So the certainty equivalents do capture the insurance effect, but you also need to capture the way that how we aggregate the certainty equivalents over time needs to be affected by uncertainty as well. And what's even harder is that you can't do that adjustment offline sort of separately, like taking it from the literature, because that adjustment itself depends on the climatic and economic uncertainties that you're trying to value. That adjustment needs to be endogenous to the same things that you already used to create a certainty equivalent. So this approach of sort of just turning it back into a conventional easy Ramsey formula isn't going to quite work either. There are two approaches that can work. So the first one is what was highlighted in the previous talk. And this differs from what I just suggested in that, sure, you're calculating climate damages scenario by scenario, but now you discount within the scenario. So you take the Ramsey rule within that scenario, the simplest, straightforward Ramsey rule, but the growth rate of consumption is scenario specific. Once you've discounted within the scenario, you can then aggregate across scenarios, whether weighting by probability or however else you want to think about it. And then you get the expected value of reducing emissions. And this does work. And you can show analytically this does work. The critical thing is the discount rate has to vary by scenario. If it doesn't, you miss the precautionary effect. And this might seem utility free to some people, but note that these formulas do imply a utility function. The last or the other approach is that in each scenario, you could just calculate marginal utility loss, discount at your pure rate of time for reference without any Ramsey formula. And in that case, you're implicitly getting everything correct either. These two approaches are going to be equivalent if you implement them equivalently. And each one of them needs a utility function. Just one makes it explicit, one makes it a little implicit. So recommendations going forward. There's two main ones that I have. So my prior and the results of my paper cohere with that prior. That the damage uncertainty is likely to be the most important. And part of that is just because we're so deeply uncertain about damages. And part of it is because damages literally are directly the marginal loss from emitting. So we need to converge in distributions to use. There's no clear distribution to use. I use the results of a survey. Others might use econometric models uncertainty, which is really more sampling or statistical uncertainty and doesn't include the full functional form and such uncertainty. We need to converge on the right way to get uncertainty and on distributions we can use, much as we do have those from the science literature for the effect of warming. The second is that we need best practices for these calculations. So which uncertainties should a reasonable calculation include and which ones are kind of optional? What requirements must distributions satisfy? What kind of ways can they represent catastrophe? Are normal distributions with exponential tails okay, or are they not okay? What are our rules of the road going to be? Which numerical methods are acceptable? I've suggested 2 are not, and 2 are acceptable. It'd be nice to have just common practices around that, like we do for the deterministic social cost of carbon. And the last is, how do you report the results of your study? We need to highlight why things are happening. We don't just want a number out of a model. So we need to know what's the equivalent deterministic value. Why does uncertainty make it larger or smaller? What are the implications for the discount rate? Which part of that's a risk adjustment? Which part of that is the risk-free rate changing? And so just some sort of benchmark way of how we're going to report numbers from different models, I think would be enormously helpful for the literature. So those are my thoughts. Thank you. And I look forward to Billy's comments.
Thank you very much, Derek. You are perfectly on time. Then, for the last 20 minutes before the discussion, I give the floor to Billy.
Thank you, Christian, for inviting me this morning or this afternoon to talk with everybody. As you'll see, I think this fits in very well with the presentation so far. This is going to be a return to a quantitative numerical analysis. And I think the best way to think about this is in Frederick's and Oled's presentation when they introduced their methodology 1, where they suggested doing a massive uncertainty analysis, and then they opted for methodology 2. We're going to stick on methodology 1 and just do kind of a massive uncertainty analysis. And the approach that I'm going to be talking about today is basically what was adopted by the U.S. government, or has been proposed to be adopted by the U.S. government at the end of last year, in the methane rule that was released in November. And Frederick alluded to this. And that approach is also based on some recent RFF research that was also published last year, which was largely adopted by the EPA in their proposed new methodology. With the exception that they added a couple of different damage functions, which I will mention. And lurking underneath this is the discounting approach that we've all been talking about, and that Derek was just mentioning, which is that we basically create thousands and thousands of different scenarios with different economic growth, as well as different damages from climate change. And those are used to set use a Ramsey rule to basically discount each of those scenarios differently when we look at the marginal damages on top. So just to highlight the, let's see here, how do I get this thing to move? Okay, so I mentioned this is what was recently announced by the EPA. This is the regulation that was released at the end of last year, if people are interested in going back and looking at it. but this has the results that I'll be talking about at the very end of this presentation. And this is the article that also was released last year, which talks about the approach that we use through the different steps, and I'll be outlining that approach in just a moment. And you'll notice that this paper has a whole lot of authors, and I just want to acknowledge that. This was a huge team that put together these new social cost of carbon estimates, really led by Kevin Rennert and at RFF, and David Antoff at Berkeley, but a very large team. The discounting piece was really work that Brian Press, Richard Newell, and myself were involved in. So just to back up, this was kind of implicit in what Frederick and Aud were talking about, and Derek. Basically, the way we go about calculating the social cost of carbon is through what you can kind of think of as 4 modules. The first module is socioeconomic projections of emissions, income, and population. The emissions are important in order to drive the climate module, to figure out the temperature change upon which, and sea level rise and ocean acidification, upon which a pulse of CO2 is layered in order to figure out the marginal damages from 1 ton of CO2 emissions. Then you go to the damage module, which, as a number of people have talked about, frequently requires the level of economic activity and population in order to do those calculations. But that leads to, as you can kind of see in this picture right here, a baseline distribution of outcomes. And then when you have the pulse of CO2, you have a slightly different pathway of outcomes. And here the uncertainty is stylistically represented by this shaded area. And this shaded area is going to include both the climate uncertainty, it's going to include the damage uncertainty, and it's going to include the socioeconomic uncertainty in emissions and economic activity. The last step is to discount the difference between the pulsed damages and the unpulsed damages to figure out the discounted marginal damages. And as I mentioned, in each of these uncertain states, we're going to want to use the level of economic growth to determine the discount rate through the Ramsey formula that people have been talking about. Here, I'm just going to probably emphasize a bit more the socioeconomic and the discounting module in the rest of my comments, just because those are the pieces that determine the discount rate, which has kind of been the primary topic of conversation. But just to walk through these pieces and what we did. So these are all stylized pictures here, but these are real pictures of distributions here. Here you see the projections that RFF put together of population, economic growth, and global CO2 emissions. I won't really go into much detail except on the middle panel in just a second, but I'll note that the population projections were the same sorts of uncertain projections that are done by the UN every year using their stochastic demographic model. And I'll note that the emission scenarios, which are actually kind of an interesting topic unto themselves, were derived entirely from expert elicitation, because the idea is that we wanted projections of emissions that reflected not just the policies and historical patterns, but what people thought would happen in the future. And we had a number of experts, and I can share with you that information if people are interested. But interestingly, it does have us rapidly decreasing emissions kind of in this central case, although it does not reach 0 emissions under the median case for quite some time. Okay, sorry, I need to go over here. Okay, so I mentioned I would talk for a second about the economic growth scenarios. So this is a combination of projecting historical patterns, but actually overlaying expert judgment. And the interesting thing I would just point out here is that the pattern of growth, and what you're seeing graphed on the vertical axis here, is the compound growth out to some year in the future. So when that growth rate declines in the future, that's actually the compound growth rate out to some distance, like 2100, 2200, 2300. And the thing that I like to highlight in this graph is that the range of uncertainty about future economic growth is actually much wider than most previous projections suggested. So if you used the IPCC's shared socioeconomic pathways, you would not have predicted nearly the uncertainty in the distant future that is suggested either by the data or by the experts who thought about these sorts of things. In particular, there is probability of low, i.e. zero economic growth over the next 200 years, 300 years, as well as the possibility of high growth as well. And again, if people are interested, I can share with you those documents, or you can see the references there on the slide. When you get into the climate module, I forget whether it was, I think it was, who was talking about, I think it was Frederick and Ode. The model that was used in this analysis is actually the FAIR climate model, which tries to address uncertainty not just about the equilibrium climate sensitivity, but also now I'm blanking on the name. The speed at which you get to the equilibrium, it has a name, and I'm forgetting what that parameter is, but that's actually a very important parameter as well. And so the FAIR model actually captures both of these features in a fairly simplistic way that allows for simulating very wide ranges of uncertainty quickly, which is what we've done in these graphs. Okay. So finally, just to mention the damage functions, because this has been talked about quite a bit. So the purpose of this analysis was to inform U.S. government policy and how we do cost-benefit analysis in the United States. And generally, the important thing is to have fairly rigorous statistical analysis and data basis for those for that analysis. So all of these studies, at least the first two, are based on fairly specific econometric models of estimated temperature damage relationships. And you can see on the right the kind of calibrated damage functions that went with the uncertainty associated with those different damage functions. So the middle one is the one that we actually developed at RFF. The first one was developed at the University of Chicago, and the third one is a meta-analysis that was published several years ago by Thomas Sterner and Howard. But what you'll see is that these damage scenarios do not have the kinds of dramatic damages that you might see, in the sense that there's not like 50% loss of GDP or something like that. These things go up to maybe a 20% loss of GDP in some cases, but not, totally wiping out the economy sorts of things. Okay, let's see here. So now I just want to talk about the discounting, and I guess this is going to be a little bit of repetition relative to what you've heard before. But as other folks have mentioned, the basic idea is to have a discount rate that varies by state of nature based on the growth rate in that state of nature. So here, I apologize, I think my notation has changed relative to the earlier presentations, but the basic idea is that there's some pure rate of time preference rho, and then there's some discounting due to economic growth based on the parameter eta, and that varies across the kind of compounded growth rate up to time t in each of these uncertain states of nature S. And we simulate all of these things simultaneously, so we're estimating damages in each scenario and an appropriate discount rate in that same scenario. And this, as Derek was saying, captures all of these precautionary features that you would want in your social cost of carbon. These are formulas that you saw some version of this, I think, in both the previous presentations to some extent, namely that you're going to discount the future based on pure time preference, as well as a discount factor related to the change in consumption from now until the point in the future when you're discounting. And the important thing I would just note is that this consumption in the future state is going to include both the stochastic growth up to that state, but also the climate damages in that state, not the marginal, but the actual baseline climate damages in that state as well. And this can be simplified to the discounting expression in the previous slide. So then the question becomes, how do we get these rho and eta values for the discounting process? And here I'll just kind of summarize. This is based on the procedure that Richard Newell and Brian Preston and I came up with. And the basic idea is that we have studies that have looked at term structures of discount rates. And the most recent example is a couple of papers by Michael Bauer and Glenn Rudebush. And what we did was we took the risk-free rate that would come out of a stochastic discounting formula, and given the uncertain growth rates that we have that I've been talking about so far, and we picked the rho and eta values that actually allowed us to match the risk-free term structure that Bauer and Rudebush came up with. And we did it for different calibrated near-term discount rates. So you can kind of start the Bauer and Rudebush term structure 1.5% discount rate, 2%, 2.5%, 3%. And depending on what you start as your near-term discount rate, you would come up with different values of rho and eta in conjunction with our growth rate projections to kind of match that term structure. So you can see that for a 2% discount rate, which is kind of the central case that the US government seems to be going towards right now, you would get a rho of 0.2% and an eta of 1.24. And that is the rate that I think we'll see. So here is just a table from that EPA report that I mentioned that came out in November. And you can see 3 different discount rate scenarios, near-term discount rate scenarios. And the center one is 2%. You can see 3 different climate damage functions. The Chicago model, the DSEM, or the Climate Impact Labs, the RFF model, the RFF Berkeley model, GIVE, and this meta-analysis by Howard and Sterner. And here you can see the different social costs of carbon that come out of this fully stochastic approach for different years of emissions. So 2020, using all these 3 different models, it's the social cost of carbon is somewhere between $190 and $200 a ton. As you go forward in time, the social cost of carbon gets higher. As Frederick was mentioning, if you actually look at how fast the social cost of carbon is rising over time, it's only at about 1.5%. So it's actually rising at less than the discount rate, exactly as he was talking about. The last thing I just want to highlight, and then we can get into the Q&A, which I'm excited for, is that at these levels of climate damages, that is, close to 200 or in excess of $200 a ton, in some sense, some of the questions we've been asking in the past become less important, because at $200 a ton of carbon dioxide, that is basically arguing for net zero emissions. You can fully decarbonize the economy by most estimates at these sorts of carbon dioxide benefits. So a lot of the questions that I think we had in the past, when we had very low social costs of carbon and motivated a lot of concern about discounting and the damages and uncertainty, actually may be giving way to the reality that we now know that we should be decarbonizing. And there's a question about how quickly we can do it, but that question of whether we should be going to net zero has actually been largely removed, I think. So with that, let me stop and turn it back over to Christian. Thank you.
Thank you, Billy. Thank you very much. So let me stay with your conclusion for a minute. I think the 3 presentations converge to the idea that taking into account of risk and uncertainty imply an increase in the social cost of carbon, and this increase in social cost of carbon is large enough to imagine that indeed, contrary to the kind of messages that we got from DICE and William Nordhaus from so many years, that the optimal increase in global temperature could be above 3 degrees Celsius. Now economy seems to be reconciled with the idea of zero net emission, and the 2 degrees Celsius target. So that's good. I also take from this tree presentation that indeed, in theory, uncertainty does not necessarily reduce the discount rate and therefore increase the social cost of carbon. Because it really depends upon the side of the beta and whether reducing emissions of CO2 does not only reduce the expected damage, but it also reduce the expected damages in the war state of nature. So therefore providing a edge benefit or insurance benefit for future generation. And so that's where probably there are still some discussion to have. I mean, neither Billy nor Derek presented details about that, whether in their model is beta positive or negative. And that's, I mean, in the tree presentation, in fact, it was interesting to see that the tree presentation were aligned with the idea that we could, rather than using the beta terminology of the capital asset pricing model or the consumption-based capital asset pricing model, we should use a stochastic discount factor approach, which is perfectly fine, but maybe some kind of black box, because you do Monte Carlo simulation with a lot of state of nature, and then you use a specific discount rate for each state, and you estimate the net present value, and then eventually you take the expected net present value. So that's, if you don't at the same time provide some information about the statistical relationship between the marginal damage and aggregate consumption in different state of nature, I mean, it could be relatively hard, and that's probably the main critique I can do with this EPA report. I mean, the EPA documents of last November. It's not clear to me that in the model you use, fighting climate change as an insurance benefit for future generation, and that's explained why you get such a large, when compared to previous estimation, I would say such a large social cost of carbon. So could any one of you want to make an elaboration about this? Derek or Billy? Maybe Billy, you are the first. You are my target there.
Well, I can say, I mean, one thing, I mean, a big difference, I mean, I went through it quickly, but, you know, the main reason the social cost of carbon is high now in the United States is actually the shift in the underlying near-term discount rate. So, you know, I think if you did the analysis using a 3% rate, you would have a social cost of carbon of maybe $80, $70 or $80 initially. The fact that it goes all the way up to $180 is not because of uncertainty. It's because we are now using a lower calibrated discount rate. So that is important to understand. The other thing I was just going to mention is that, you know, in the modeling that we're doing, I'm hesitate to say all, but I'm pretty sure like almost all of the damages are proportionate to economic output. So it is implicitly assuming a beta of 1.
Okay. Interesting. Thank you very much. We got one last one you had with Giang Fung.
Yeah, thank you. So my question, first of all, thank you for the presentation, which have to determine the price of carbon. But my question is that now, of course, it's already a very difficult issue, but it seems that at this stage, we determine the price of carbon at a global level. But it seems to me that we cannot charge the same price for every country because the contribution of carbon are not the same, and their living standard are not the same. So it seems to be unfair to charge them the same price. So have you ever thought of a solution to this?
Thank you, Giang. So this question is about whether to calibrate differently for the Ramsey rule, I understand, for different countries, given different perspective of development and maybe different attitude toward time and risk. I don't know. Does anyone to reply among my panelists?
I have something I'd like to say about that, but I'd be really curious about what the others think as well, because my comment's a little orthogonal probably. So there is work that tries to incorporate aversion to inequality and such into the carbon price. The basic tenets of efficiency of the carbon price should be the same everywhere, but there are obviously reasons why you might not want that to happen. So I'm curious what the other two think about that in the context of their models. I am doing something that is on the lines of what you're thinking, though, where I'm thinking instead of mitigation policy, how should you target adaptation funding? And they're trying to trade off, basically thinking about a mean variance frontier. Like, so what if you have some concern for inequality of climate damage outcomes around the world, but you also have a concern for global efficiency? How would you target funding differently based on the relative weight you attach to these things? And what does the trade-off look like? What's your variance minimizing portfolio as you sort of reduce your required benefits from abatement? So that there is that kind of approach where you could treat it as a portfolio problem and thinking about the trade-offs between how much variance you allow across countries and what the average efficiency benefit you're going to require is. But I'd be curious to hear, especially from Billy, how the EPA thought about this and how RFF thought about this.
Billy?
Sure. Well, yeah, just to say a couple of things about how we doing the calculation and then maybe reflect on the implications for action. So, this was very much, thinking about a US policy context. It is a global, we do allow for global damages, and we do not, do any sort of weighting that suggests that $1 to a poor person in Bangladesh should be valued more than $1 to a U.S. citizen, for example. There are actually arguments, based on standing that, we should be privileging U.S. Citizens more in our own domestic cost benefit analysis, but that is not being done. The arguments for not doing equity weighting, which I think is what Derek was alluding to, are, along the lines of, if you are looking for, it kind of goes to whether or not you were looking for a social welfare function that is actually going to try to remove inequality or not. Because if you are trying to remove inequality as a policy objective, then yeah, you could value poor people's income more, or dollars to poor people more. But that has not been a U.S. A model for U.S. action domestically. Internally, we don't value poor people more heavily in cost benefit analysis. And so I guess my general answer is that we, at least in the United States, we have not looked at cost benefit analysis as a way to represent concerns about equity. I think you would probably look at the distribution across countries as opposed to trying to somehow bury that in a weight in a cost benefit analysis. So that's just kind of a reflection on how things are done in practice in the U.S. Obviously, I think from a standpoint of what the implications are for action, of course, we would not expect poor countries to be as ambitious in their mitigation. I would not, I don't know, I shouldn't speak for we, but I would not expect poor countries to be ambitious. And presumably, if you were doing the same calculation in a poor country and you had a faster economic growth rate, you would be discounting more. So, there would be a whole different sort of way of doing these things, I think, if you were trying to do it in a poorer country. So, I think that's
Thank you, Billy. So I see Frédéric and Aude want to intervene, and then Jacques Delplat and Gabriela Mundaka. Just one word on this. I mean, there is a form of incoherence in the way we model or benefit cost analysis, where we take into account intertemporal or intergenerational inequality. That's the Ramsey rule. We discount the future because we believe future generation will be wealthier than us. And that's why we penalize the transfer of consumption to these future people, whereas intragenerationally we decline using the same idea. So that's some kind of incoherence. Frédéric?
Yeah, just say that we could, of course, in the model include inequality and put some weight and see if we get at the end different carbon price for different country, but it's not practical. I mean, there is no direct application of that. What is important is to understand how we can practically implement carbon price. In one given country, the way to do that is to give back the money raised by carbon price to people. And we know that it's not only about resources or only about geographic location. For instance, in France, if we want to have an environmental policy with carbon price, we need to give back the money to people who have both low resources and who are in a geographical location where they need a car. For around the world, it's far more difficult to do that. And the only way I know about is to interconnect, for example, to interconnect carbon price markets. There was a project like that between Canada, Californian market, and also in Chile, in South America, to interconnect all those carbon price markets. But the issue was about governance. They were not able to have a common governance to limit the number of pollution permits. But I think we need to look at that in a practical way, how to implement a policy where it works. But the first best is anyway to have only the single carbon price around the world.
Thank you, Frédéric. I would not want to spend too much time on this issue of inequality, but that's maybe I agree, it's an important matter. But do you want to comment on this?
Yeah, I'm going to be very quick because it's a slightly different. It's not really social cost of carbon anymore. But if on the basis of social cost of carbon, we end up thinking that zero net emission is a good idea, then carbon budget are coming back in the room, and you can always define carbon budget that would be different across countries, and that would be also a way to look at this issue.
Thank you, Aude. So, Jacques Delplat, you were the first on my list. Do you want to intervene at this stage?
Yes, thank you. Can you hear me, Christian?
Yes.
All your models and others assume that there is a kind of hard science truth about climate change in the future, mostly from IPCC, and then we economists try to work on the discount rate. But the problem that I don't see here is the technological progress. Imagine carbon price is $1,000 tomorrow in most of the countries. That will stimulate massively technological progress in all of the technological stuff. Even in you would have nuclear power plants built massively everywhere, geothermal, all these kind of things. So I don't see in your models and elsewhere a clear relation between carbon price and technological progress, which I think is major.
Thank you very much, Jacques. So those models are equilibrium models. So I think they make those models are based on assumption on technological progress. But maybe Derek or Billy want to contribute to this.
Well, I would just say, the work that we were doing was, had a very particular purpose. It was not to it was not to define a particular policy instrument or recommend a particular policy. It was to develop a benefit number to apply to carbon reductions for any policy, and in particular for a marginal policy. So the whole way that was developed was based on our best estimate of what the future path of emissions would look like, which included all sorts of technological developments and uncertainty about those technological developments. But the purpose for the social cost of carbon was to define a benefit measure to go with a policy analysis and presumably a marginal policy analysis in the United States. And it's a totally different conversation to talk about which policies you actually need and want and can politically get. And we could have that conversation if folks want, but this was mainly about measuring benefits.
Thank you. So let me switch now to Gabriela Mundaka. You want to raise your question, Gabriela?
Thank you for the presentation. So I may ask a question that may not be part of the research that you are doing, but I was wondering whether your estimations about the carbon price determination or social cost of carbon should they take into account the mass of countries that are really implementing the carbon taxation? Does it matter the mass of countries that really participate in this mitigation climate? And that's the thinking more about the less endowed countries, right? So that are difficult for them to implement carbon taxation. So you think if only a very small number of countries are imposing carbon taxation, it's a very different scenario that if 80% are participating, in this carbon taxation. So it doesn't matter the mass of countries. Thank you.
So I don't know who want to answer this question. Just my comment on this. Indeed, as Billy just said, I mean, those estimation of carbon values are supporting a pathway of decarbonization. So we make assumption about decarbonization, and we look at what the carbon price schedule is or are compatible with this process. And of course, this depends upon which country or many countries will start to decarbonize and go more intensively in decarbonization. And of course, if Belgium would be alone to decarbonize, that would be the carbon price, which would be socially desirable for Belgium, would be very different for if all countries around the world would do the same thing. So there are some so different models make different assumptions about who will do what. And that's, of course, critically important about to determine what the social cost of carbon for specific countries. Some panelists want to complement this?
Yeah, I'll add something to this. So kind of seconding what Christian and Billy said in the last two answers, the previous two questions were about factors, technological progress, and incomplete participation of countries, and how do they affect the conversation here. And I think there's a way in which the effect is trivial and a way in which it's a much broader picture discussion. So the way in which it's trivial is the technological progress. That's just part of if you have a certain carbon price, how much does it cost to implement it? And all these models have to take a stand on that at some level. And there are better and worse ways of doing that, but it's ultimately just part of the modeling framework. Same thing with incomplete participation. It's ultimately about what are the future emission trajectories going to be? And this is something that is implicitly part of, there's some implicit stand being taken on that through the emission trajectories that Billy was describing. So there's ways in which these are just always accounted for. There's other ways in which they're not accounted for because they raise different questions than what we're talking about here. The technological progress question raises questions about how do you do R&D subsidies versus carbon pricing, for instance. And there's work in the literature I've contributed to exploring whether you need short-term R&D subsidies. Do they displace carbon pricing? Do they complement carbon pricing? Do they trade off short-run subsidies versus long-run carbon pricing? And there's a recent literature on that I think is interesting and can inform that thinking about the CCS question. On the incomplete participation, it raises questions about should you choose a different carbon price than is the social cost of carbon, because you either recognize other people aren't doing much, or because maybe you want to make them do something. And then again, you get into a different kind of model where it's more of a game theoretic question. And then that's a literature where my read is it kind of comes to conflicting answers depending on the setup. But I think where it's interesting is for raising these different questions that are a bit different. What price should you put in place? Should it account for R&D? Should it account for incomplete participation? In a strategic way, not about the actual technicalities of how you calculate the social cost of carbon.
Thank you, Derek. So we have 4 questions on the Q&A button. I see one is about how to incorporate political uncertainties and lack of commitment on future carbon pricing in the modeling of the social cost of carbon. I think it's a difficult question. I don't know how. Is there anyone put some light on this question? There are 2 questions related to the normative versus positive issue. I mean, let me reply on this. I mean, we are talking about the social cost of carbon. Basically, when we look at when we examine a specific decarbonization action, we have cost associated to that. To what kind of benefit should we put this cost into the balance? And so that's the value of carbon. So whether it imply mean, the question of whether we should make sure that everyone does that exact same normative evaluation and therefore put a carbon price, that is a carbon tax or a market for permits. It's a question which is not exactly the issue that we want to cover for this roundtable. So this carbon pricing, whether we should put in place that, I mean, this will be that has been for past session of this webinar, and certainly for future webinar session, but not for this one. So going back to the political uncertainty, does anyone want to answer to that question?
On commitment, let me emphasize that the social cost of carbon is different than the optimal carbon tax. We've been talking about the social cost of carbon, the extra damage from a unit of carbon emissions. And these are the calculations that were nicely detailed in the other talks. The optimal carbon tax should be a bigger picture concern. It's optimal in the actual world, and that it should account for R&D effects. It should account for these commitment effects over time. It should account for strategic effects across countries. And so that these kinds of effects are not in the models we've talked about, but this is they're irrelevant for the social cost of carbon, but they're really critical for the right tax to impose in the world. And I'll defer to anybody else if they have an opinion on how that should affect it.
At the end,
just to say, there are multiple reasons to do more carbon tax. Partly because there is a lack of political commitment about carbon tax. For instance, for R&D subsidies, there is a clear market imperfection because the patent duration is not enough to cover investment in R&D that may be profitable over 50 years. So this is an argument to do more than carbon tax, but also to subsidize R&D. And the fact that governments are not able to commit to a social cost of carbon and carbon tax structure over time is another argument for that. So there are a few papers on that, but to my knowledge, there is no estimation using an integrated assessment model of the optimal carbon tax and optimal subsidies, taking into account the lack of commitment. This is an open issue.
Thank you, Frédéric. Aude?
Yeah, so following up, I think there is no real consensus. You can find some literature like the one of Hassler that says that carbon tax is going to do the whole of the job, including the incentive for R&D. But as I said, there is no, I think, consensus on that. And just a small point on the way France is designing the value of carbon. So this is an official value. This is not a social cost of carbon, the way it is computed. It is based on the carbon budget, but there are some sensitivity analyses that are done depending on what the rest of the world is doing, and also depending on whether there are technological improvements that go faster than what is expected as well.
So could you remind us what's the social cost of carbon in 2023 in France?
I can tell you in 2030 by heart, which
Okay.
is 230. If you give me 2 minutes, I will tell you.
Waiting for this answer. I have a question for Derek and Billy. I mean, going back to your way of modeling the uncertainty, I mean, and compare it to what Frédéric and Aude have been presenting. In Frédéric and Aude's presentation, they put much emphasis on the fact that we need to take into account extreme events to determine, to really take into account of the riskiness and its impact on valuation. In direct models, I mean, are your results that the social cost of carbon is increased by uncertainty? Does it depend upon Gaussian distribution? I mean, do you make normality assumption there? And for Billy, I mean, I have a similar question. How do you model the uncertainty affecting growth? Do you make an assumption like geometric Brownian motion for that? My concern, if you do that, is you know, the standard asset pricing puzzles, where we know that if we use Gaussian distribution with such a relatively small degree of concavity for the utility function, I just mentioned Billy's assumption of a degree of concavity of 1.24, which is relatively small when we consider it to be risk aversion. And so how do you model long-term uncertainty in in your evaluation of the social cost of carbon, Derek and Billy. That was not very clear in your presentation.
I can briefly go if you want, Billy. You want to take more time to elaborate? I can go back and be short and get you ahead. Yeah, mine's Gaussian all the way through, and there is a chance of quote unquote catastrophe in that the damage calibration has such large variance that it is well within the spread of outcomes for consumption to reach a very low value within the next few hundred years. But there's not an explicit catastrophe. It's just a low probability draw or reasonable probability draw from a Gaussian. So it's Gaussian all the way through.
Okay, good.
I like the cumulative approach, but that's not what I used. So
okay, and Billy?
Yeah, so I mean, you're right that there are going to be some amount of risk aversion is not captured in the model because we are focused on the discounting over time and getting that correct and using a simple Ramsey formula that doesn't allow us to solve the equity premium puzzle. So that is a limitation. But I don't know the alternative to get a realistic representation of uncertainty. I mean, one of the problems with doing the kinds of things that Frederick and Aude were doing is, you need to use some sort of survey, or you need to use something to kind of get that low probability extreme event. And it tends to be more subjective. And one of the things that we were trying to do for the purposes of U.S. government policy is to ground it as much as we could in empirical data. And so that tends to just make the regulatory process in the United States more robust.
Okay, thank you. Oh, do you want to answer to this specific point? I mean, we can introduce a catastrophic event using the approach of Robert Barrault. I mean, he documented macro catastrophes in the 20th century for 35 countries and get a calibration of probability of a catastrophe of 1.7% per year with the mean drop in GDP of something like 30 or 40%. So that could be done. But
what's the contribution of climate to that? How do you estimate the contribution of climate to changing that disaster risk?
That's a good question.
And how persistent is that? Because I mean, we've had economic catastrophes. We haven't had an example where we're still poor.
Well, you in the US, but not in the other 34 countries of the Robert Barrault dataset.
No, but if you're looking for,
but if you said you have Russia, I mean, maybe not Russia, because with Russia it was even worse. I mean, with the Soviet Revolution, but Argentina, Greece, I mean, Germany, Japan.
I think there are two things that can be said. First, there is a problem probably to try to estimate catastrophe based on historical data. I mean, if we use the same data as Barrault, probably the world is not the same. The world is more global. We don't have the same type of shocks. So probably everything is adjusting in a very different way. So that's the first one. And then I don't think it prevents from looking at this scenario. I mean, that's an interesting, I mean, you need to have very different representation of the world if you want to understand what's happening. So I think it's a good idea to have a representation where everything is fine and another one where you do have a catastrophe. And then all the question is what type of probability you put on each of them. And it's always possible to put a super small probability on that risk of catastrophe. But it's still interesting to see what's happening in this case. And I not really comment this picture on one of my slides, but if you compare the importance for the insurance value of a project of such catastrophe compared to very small idiosyncratic risk, I mean, that's amazing how a very small risk of catastrophe has a lot more value in some way than a very small idiosyncratic risk.
I saw that too, because as I look further out, the social cost of carbon include more years, my Gaussian makes the equivalent of catastrophe is more and more likely, and the cost of carbon keeps going up, even though discounting is working against that, just because the spread of things is getting so large farther out. But this and Christian's earlier question to Billy really reinforced my desire just to have norms about, what experiments do we think are the right ones to be run, and what are reasonable calibrations around them. I feel like there are similar norms in, for instance, the equity premium literature, but I don't think we have good norms in this literature about how to show marginal damage and emission correlations or whatever it might be. And that would be really helpful to just have reference points that we could then begin varying and doing more with rather than changing multiple things at a time.
One thing crossed my mind. Why not calibrating the model probability of catastrophes by looking at all the science fiction movies? On one side, put the dystopian movies, and the other side, the utopian movies, and see what's the proportion of the first compared to the second. But not. I mean, I'm not sure But clearly, I mean, in our culture, it's clear that we have somewhere in our mind a situation where civilization disappear and we go back to Stone Age or whatever. I mean, the day after, or so that
The box office receipts act like prediction market prices.
Yeah. So time is over. Let me raise one last question, and I'm sorry, it's so Billy. What's the probability of having a social cost of carbon of $190 per ton of CO2 next year in the US?
You mean for cost benefit analysis or implementing like a
social cost of carbon? What's the status? What's the legal status of the EPE report you were discussing in your presentation? Is it an official document? Is it supported by the EPE? I mean, is it supported?
Yeah, it's supported by the EPE. It's a proposed rule, so I think it has to go final this year. But just to emphasize that having a social cost of carbon of $190 simply means that cost benefit analysis in the United States will proceed that way. It doesn't mean we're going to do anything, have any actual regulations. It just means that that'll be what's used for the analysis. But I think it's very likely. I think it's, and I think the goal is to make that robust so that it won't fluctuate when a new administration comes into power.
That would be game changing, and France was above the US in terms of a climate ambition over the last few years. But I must say that you are reversing the table now. That's impressive.
Well, again, I would just emphasize having a high benefit number doesn't actually translate necessarily to policies. I mean, the IRA was obviously a very impressive piece of work, but in terms of regulatory action, I think that's still going to be a very hard process in the United States.
Okay, so you know what? I'm impressed by your capacity, you and I, to change the world by providing rational argument to raise the social cost of carbon, and I find it quite satisfactory. I mean, good. I'm happy to be an economist these days. Okay, my friends, time to leave this meeting, and we got almost when at the top we got more than 200 participants. I'm quite impressed by the participation, and thank you all. See you next time for the 13th episode of the webinar next month. Bye bye.
Great to see everyone.
Likewise. Thank you.